Welcome to the Walton Pi. Today we're going to be talking about sequences, so we're going to talk about what they are, how we can use them, as well as what the limit of different sequences would be. So a sequence is just an infinite list of numbers with a specific ordering. So numbers can repeat in the sequence, so for example 1, 2, 3, 4, 5, 6, 7, and so on, that would be one sequence. So would 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and so on. Both of those are sequences. They're an infinite list of numbers. The numbers can show up multiple times, but there's a specific order to the numbers that they show up. So that's the difference between a set and a sequence. A set, there's no order. A sequence, there is an order. So some sequences are defined by listing out terms and then extrapolating the pattern. So saying, from this, the pattern is going to be pretty straightforward. Kind of like the 1, 2, 3, 4, so on. That pattern is pretty clear. So another example would be 1, 4, 9, 16, 25, 36, 49. So the sequence of perfect squares. That's an example of one. But then we could also define a rule that then defines the sequence. So we might see it as a sub n, or inside the curly braces, or a sub n inside parentheses. Those are the two common ways to write a sequence. But we might define it as a sub n is equal to n squared. So that says the nth term in the sequence is just going to be n squared. And this is the same sequence as before. The first term, that's 1 squared, which is 1. Second term is 2 squared, which is 2. Then 3 squared is 9, 4 squared is 16, and so on. And so both of these are two different ways to define the same sequence. We could also define it using what's called recursion. So recursion is a process that repeats itself in order to compute the next term in the sequence. So one place that you might see this is in computer programming, but we can use recursion to define a sequence. So we might define the first few terms and then define a rule that uses recursion to then find the next terms. For example, we might say that a sub 1 is equal to 1, and then a recursive rule says that a sub n is equal to a sub n minus 1 plus 3, meaning take whatever the last term in the sequence was and add 3. That is a recursive way to define the sequence 1, 4, 7, 10, 13, and so on, because the rule is saying take the previous term and then just add 3. That's what the recursion means, and that's what the a sub n minus 1 means. That says look at the previous term in the sequence. So the Fibonacci sequence, that is one example of a sequence that is defined recursively. So if we define a1 to be 1 and a2 to be 1, then for everything else after that, we just define a sub n to be a sub n minus 1 plus a sub n minus 2. So you just take the two previous terms and add them together. So it'll go 1, 1, then 2, because that's 1 plus 1, 3, because that's 1 plus 2, 5 is 2 plus 3, and so on, to get 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. If you're interested, I actually once tried to see how many terms of the Fibonacci sequence I could say in exactly 11 minutes and 23 seconds. Why did I choose that? Well, that's 1, 1, 2, 3, so the first 4 terms of the Fibonacci sequence. And it's surprisingly hard to be able to say them without accidentally messing up on any of the numbers. Feel free to check out the video that'll show up in the card, and go ahead and try and read alongside me and see how many you can do without messing up. Okay, so we can also talk about what's called the sequence limit. So a sequence will have a limit L if we can make the terms a sub n sufficiently close to L if we have n sufficiently large. Now, that's the formal math definition without the epsilons and stuff, but what this really means is it says a sequence has a limit if eventually far enough down the line in the sequence, there's a point where every single number in the sequence is really, really, really close to L. If that's the case, then we have found the limit of the sequence, because everything is really, really close to this same number every single time. So in other words, and this is the epsilon definition, the limit as n goes to infinity of a sub n is equal to L if for every epsilon bigger than 0, there's some corresponding n bigger than 0, such that for every a sub n after that big N, the absolute value of a sub n minus L is less than epsilon, meaning that it's as close as we need it to be to L. So, for example, the sequence 1, 1/2, 1/3, 1/4, 1/5, and so on, where every term is just 1 over n, that limit is going to be 0. And the reason for that is we are going to want 1 over n to be less than epsilon eventually, and so then we are going to just go through and solve that. So if for any epsilon bigger than 0, we just pick our big N to be bigger than 1 over epsilon. Then if little n is bigger than big N, then 1 over little n is less than 1 over big N, which is less than 1 over the quantity 1 over epsilon, which is a fancy way of writing epsilon, which means that the limit of this sequence is 0. Which makes sense, because if we have 1, 1/2, 1/3, 1/4, each number is getting smaller, but they are never going to become negative, so the limit is going to become 0. I hope this video was helpful in understanding sequences. Please check out some of my other videos, and if you're not subscribed, please consider doing so. It really helps me to be able to continue to make these videos. Have a great day and good luck with the rest of your math.